Yes.
Yes. Okay, that's okay. So, what is the concept? First of all, we start with the mass or material balances. Then we will have also energy balances. Somehow, I think you have some background knowledge about balances, at least the energy balances, maybe less the mass balances. But of course, we will, in any case, we need to go deeper with the mass balances because it's the important conservation law that we need to consider when we have a process with one or more inputs and one or more output or products. So in general, we can say that the total mass of input is equal to the total mass of output. And this, of course, is based on a law conservation of mass that is based on the fact that the mass can neither be created nor destroyed because we are not considering cases in which there are nuclear reactions. Of course, in that case, you can have conversion from mass to energy, but in ordinary chemical processes, but also mechanical processes, we don't have such a situation. So we can't say that in terms of total mass, there is conservation. Of course, this is important. It is the fundamental law that we have to consider when we are designing or operating any process, because we cannot complete the design or the analysis of an existing process without considering the relationship between inputs and outputs on the basis on material balance equation. And actually, we need to do this for the whole process that we can consider as a black box, as reported in the picture. So without looking inside into the tail. But this type of approach, of course, has to be followed also for single process units that are part of the whole process. So we need, in any case, to satisfy balance equations. Now, so what are the learning objectives that we have on this particular topic? So we need to understand and acquire methods to organize information about the process variables. Yesterday, I introduced and recapped some of the main process variables that we will make use of them today and in the following part of the course, of course. And once we have these, we need to set material balance equation and solve the equations in order to estimate the unknown variables. So as in all the mathematical problems, we will have input data and unknown variables. In any case, these will be referred to process variables. So if we want to depict a pathway, a sort of procedure, a process that we need to follow to do this, we will need to, first of all, draw and fully label a flow chart. That is actually the schematic representation of a process. Choose a convenient basis of calculation. Then for multiple unit process, identify the subsystem for which balances might be written. Perform the degree of freedom analysis for the overall system and each possible subsystem. So in case we will have several variables, we have to consider this. Write the equation to calculate specified process variables. Perform the calculation equation. So this is the general procedure that we will follow. Of course, we will proceed step by step, starting from easier situation, and then we will move to more complex case. So, of course, we will start from simple flowchart in which we have only some inputs and some outputs, and see how to approach the problem. And then, of course, we will move to more complex flowchart in which we have a combination of process units. But before doing this, let's classify the type of balance equation. Okay, so we can write two different type of balances in general. The first type is differential balance. That is a balance in which we refer to what is happening in a unit, in a process, in a system at an instant in time. So this means that each term of the balance that we write is in term is a rate. So is, for example, a rate of input, or we will see a rate of output, or we will see eventually a rate of generation in the case in which we have generation of mass. And so this means that the unit will be a process quantity by the balance quantity that in the case of mass balance is mass divided by a time unit. So it will be, in case of mass balance, kilogram per hour, kilogram per second, kilogram per day, and so on, tons per year, and so on. Of course, if we are doing balances on different things, like we will see with the simple example, it could be another type of balanced quantity, but in any case will be for a unit, for a time unit. So, and this is the type of balance that we usually apply for continuous process. In particular, we will refer to steady state condition, but this is not always the case. So this is the first type. Then we have the second type of balance equation that are instead integral balance equation, in which we are following what is happening between two instants of time. So an initial time and a final time. And so in this equation, each term is an amount of the balanced quantity, and the unit is the balanced quantity itself. So is the unit of the balanced quantity. So if it is a material balance, this is basically mass, so it's kilogram, for example. Of course, if we are doing a population balance, will be people, number of person. So this type of balance is used for batch process. The batch we have seen yesterday is when we have a sequence of operation that are occurring for time intervals. And so in this case, of course, we will need to relate what is happening at two different instants of time. That could be, for example, at the beginning of one process step and at the end of that process step. For example, if we look at step 3, that is the final one in this picture, we can consider, for example, the two different moments. One is when the input take place, and the other one is when the product is withdrawn. Okay, actually, if we are considering this, we are considering three different steps, not only the final one. Okay, because we have okay, if we are isolating the 3 steps, that was filling, transformation process, at the discharging or withdrawing. We can make an integral balance, for example, for each of these steps. That could be, in the first case, initial time when the filling is starting, and final time when the filling procedure has ended. In the case of the transformation process, that could be a chemical process or something else. It could be initial time step and final when the process has been completed. And the same for the final, step 3, it is initial time of the discharge and final time of the discharge step. Now, let's consider this situation. So we have a process unit, okay, and in which we have a stream entering. It's a material stream made of a certain amount of kilogram of methane per hour. And then we have another stream leaving the process with another mass flow rate that is m dot out, again, kilogram of methane per hour. Now, if the two numbers, so the flow rate in and the flow rate out, actually here there is a mistake, I think. Yeah, it should be m out. Let me correct this. Okay. So if we have this case, it seems to violate, not to respect the conservation law that we declared before. So how is it possible that the mass flow rate of methane in output is not equal to the mass flow rate in input? Do you have an idea on this? Actually, I spoiled something because showing the full slide. In any case, go over, Diana, please.
Oh, I missed it. Okay, maybe.
Ah, that's good.
Maybe because there is a transformation. So we have in input methane, but maybe something will change here.
Okay, what type of transformation do you think of?
I don't know, maybe hydrogen can be something, can do something else.
Yeah, but okay, what type of transformation? A physical transformation, a chemical transformation?
Chemical.
Pardon?
Chemical?
Chemical, yes, could be chemical. So this is could be one explanation for this non-balanced situation. So it could be that methane has been converted, for example, has been oxidized by combustion. Okay, so this is a burner, and so this means that the methane becomes carbon dioxide and water. Okay, that is actually the chemical reaction of oxidation for methane. This is one possible explanation. That's good. Any other possible physical explanation for this unbalance?
Maybe one step for the process, there is a problem with a sensor. For example, in the input, we can have a sensor malfunctioning, and it could be a cause.
This is a very good point. Exactly, because of course when we are just drawing the box on the slide, but this corresponds to a real unit. So in order to have a figure number about the mass flow rate, we need some instrumentation, a sensor measuring the mass flow rate. So a possible explanation could be that one of the two sensors, the one measuring the input flow rate or the output flow rate, is not working properly, and so we are our reading is not correct, and so this could be an explanation for this inequality. Very good. Any other possible explanation?
Maybe
there is an accumulation of, sorry.
Go.
There is an accumulation of mass inside the process.
There is an accumulation of mass. This is also another possibility. So this means that we are not completely at the steady state. Okay.
Exactly.
Or maybe
this is again, yeah. Please.
Maybe not a perfect closed system. So we have some loss of mass of material.
Very good. Very good. Also this is very good. We could have a leakage. What is a leakage? That is actually we are losing some material in an unexpected way, maybe because this is not a closed system. So this means if this is the case, it means that the sketch we are representing is not complete because there is an additional output stream that is the leak that is not reported in the picture, and so this could explain this apparent inequality. Okay, very good. So in fact, they have the list of possible explanations. The measurements are wrong that we covered. Methane is leaking from the unit. Okay. Methane is being consumed as a reactant, or it could be also generated, of course, because I've not said in which sense this inequality applies. Of course, if the mass flow rate in output is lower than the mass flow rate in input, the methane is being consumed. If it is the opposite, so if we found more methane than we input into the process, there is some chemical reaction occurring, generating methane. So, okay, very good. And then methane is accumulating in the unit. For example, there are some possible absorbing surfaces. So the wall or something inside the vessel. The vessel is not empty, but there is, for example, a solid structure that is able to absorb the methane. Okay, like a sponge that absorbs air. Okay, a different mechanism, but in principle. Okay, so this means that we need to consider this possibility when writing a material balance on a species. So before, in the previous slide, we were talking about total mass balance, and we were saying that total mass in input is equal to the total mass in output, and there is no doubt on this. But if we are referring instead to a single species, a single chemical component, we can have a situation that is a little bit more complex than this. Okay, in particular, so if we consider the so-called general balance equation, we can put all together all these possible terms in a way that we cover all the situation. So in this equation, and this applies for a general process, process unit, a collection unit, and so on, we can write the equation in this general way. So we can have an input plus generation is equal to output plus consumption plus accumulation. So input and output are very clear. So it's what is enters through the system boundaries and what leaves through system boundaries. Then we have the generation and the consumption term that are two opposite terms somehow, because generation is we are producing material inside the system. Consumption is that we are consuming material within the system. Okay, and so in fact, we find these two terms, one on the left-hand side and the other one on the right-hand side. And then we have accumulation. So accumulation refers to the possibility to increase the quantity inside the system. So what is called a build-up. Okay. Now we can write this in the first form, like input plus generation is equal to output plus consumption plus accumulation. But eventually we can also move the term, move all the term except accumulation to the left-hand side. And so we have input plus generation minus output minus consumption equal to accumulation. So the difference between input and output and plus the difference between generation and consumption gives the accumulation. Okay, so this is the general balance equation. This applies for mass, but we will see that this general balance equation will apply also for energy. Now let's make a simple example that actually is not referred to a chemical process, but to the population. So it's a population balance in a city. So we have that each year 50,000 people move into a city, 75,000 people move out, 22,000 are born, and 19,000 die. So we can write a balance on the population of the city, just applying the general balance equation. So we have the input, that is the 50,000, the generation, that is the people that are born, so 22,000, minus the output, so those that are living, 75,000, minus 19,000, that are those that who die. Okay, and so we have here the accumulation. So the accumulation in this case is negative. Okay, is minus 22,000. So the population decrease of to 22,000 inhabitants per year. So it's a very simple and trivial example, but it's just one way to apply this general balance equation. Of course, if we move to the to next step, actually there is something wrong in the order of the writing. It's okay. So if the balanced quantity is total mass, so we have said this as a first example, and we consider that the total mass is not created nor destroyed. What we have in this case, we have that, of course, there is no generation and no consumption. And so we can write that we have input equal output plus accumulation. This is also the case when we are writing the balance on a chemical species, so a chemical component, but there is no reaction taking place. So this means that the chemical component is neither a reactant nor a product. So also in this case, generation and consumption are equal to 0. And so we can write this as input equal output plus accumulation. Okay, so this actually final equation, we don't need this. There is a mistake here. Okay. And also the order, but I will correct this after. Okay, also here, what happens? Okay, it should be this actually. So this is the combination. So the first two cases are the one that I already mentioned. Then in what is another particular case, starting from the general equation. So if we have the system at steady state, accumulation is 0, and so input plus generation equal output plus consumption. Now, in the case in which we have one the first assumption. So we are considering total mass and the system is at steady state. We have that input is equal to output. But this is also the case in which we are writing a balance on a non-reactive species and we are at steady state. So input equal output applies for either the case of the total balance on total mass at steady state, or for the case of non-reactive species at steady state. Okay, so these are simplification that we have on the general material balance equation. Okay, so if we want to summarize, these are the equation for these two cases at steady state and for total mass or for the mass of non-reactive species at steady state. Now, let's consider an example instead on a process. Now, what appears here that we have a description and a flowchart. So this is important. We will see that we have to be able to draw the flowchart starting from a description. Of course, in this case, it's very simple. It's just a unit, but we will see this also for a more complex situation. So we have that 1,000 kilogram per hour of a mixture of benzene that we call B and toluene T, containing 50% of benzene by mass, is separated by distillation into two fractions. So it's a separation unit operation, we will say. The mass flow rate of benzene in the top stream is 450 kilogram of benzene per hour, and that of toluene in the bottom stream is 475 kilogram of toluene per hour. The operation is at steady state. Write balances on benzene and toluene to calculate the unknown component flow rates in the output stream. Okay, here we have everything already done. So on the left, we have the, sorry. Okay. Here we have the, on the left, the sketch of the process unit, that is just a separation unit. And we have the input entering and two output stream, one on the top and the other on the bottom. So from the information that we have 1,000 kilogram per hour. And we know that 50% of benzene by mass is entering. So this means that 1,000, we have 500 kilogram of benzene and 500 kilogram of toluene per hour. Then the other information is that we have on the top stream 450 kilogram of benzene that is reported here on the top stream, while in the bottom stream we have 475 kilogram of toluene per hour. So we don't know instead how much toluene is leaving the top and how much benzene is leaving from the bottom stream. So we can write these two unknowns as M1 dot and M2 dot in this case. And we can apply the general balance equation with the simplification for this case. So we are at steady state and there is no generation or consumption of our chemical component because this is only a separation unit. Okay, so we can write a balance on benzene and a balance on toluene, and eventually we can write a total mass balance. So if we write the benzene mass balance, So we have 500 kilogram entering. This is equal to 450 kilogram that are on the top, plus m.2 at the bottom. So it's very easy. We calculate that m.2, that is the flow rate of benzene leaving in the bottom stream, is 50 kilogram per hour. Similarly, we can write the balance equation on toluene. So we have 500 entering, and leaving we have m1 m.1 in the top and 475 in the bottom. So m.1 is equal to 25 kilogram per hour. Of course, we can also write a total mass balance considering all the mass flow rate of all the two components, both components, entering 500 plus 500, equal to what is leaving the unit. So it's 450 plus m.1 plus 475 plus m.2. Clearly, this third equation is given by the sum of the previous two equations. Of course, we have to sum the terms, all the terms that are at the left-hand side, and all the terms that are at the right-hand side. So, okay. So in this sense, the third equation is redundant with respect to the solution of this set of equation. Because of course the third equation is a linear combination of the first two equations. So it is sufficient to consider only two of the three equations to solve this system. And of course we will state this better later in a general way, but this is very intuitive here. Okay. So I can write either the balance equation on the two components, or alternatively, I could write one balance equation on one of the two components and the total mass balance equation. In both cases, I will have two equations into unknown variables. So the system is well posed. Okay. Any question on this? Okay.
No, it's clear.
Okay. Now, of course, if we want to generalize, we could also write all this equation in symbolic way. So instead of using, in the previous case, what I made intuitively was to report numbers for the known variables and symbol for the unknown variables in order to highlight what are the unknown variables to derive. But of course, if I like, I can write also the system of equation in a completely symbolic way. Of course, if I want to do this, I need to change the notation. And so, for example, I need to number the stream. So the input stream is stream number 0. And the other to the top stream is stream number 1, and the bottom stream is stream number 2. And so I will use this number as a subscript for each mass flow rate to refer to the stream, and then a second subscript could be referred to the chemical component, for example. And so in this sense, I could rewrite the equation as m.0b is equal to m.1b plus m.2b. This is the benzene mass balance equation. Then we have for Toluen m dot 0t equal to m dot 1t plus m dot 2t. And finally, the total mass balance, that is the sum of the two. So as m dot 0b plus m dot 0t equal to m dot 1b plus m dot 2b plus m dot 1t plus m dot 2t. And in bold character, in bold font, I highlight the unknown variables. Okay, so this is an alternative way. Even if we will see that for, this is the more formal way of writing balances, but for practical purposes, the first intuitive approach in which we report all the data that are known in terms of number, it's of course more direct, more straightforward, and so could easy the solution of the problem. Okay, in this case is very simple, but this applies also for more complex flowcharts. Now, let's see what happens instead for the integral balance. I just want to ask you one thing, because on my computer I don't see the entire slide, because there is the lower bar that is overlapped with the slide. Do you see it the same way, or is it just a matter of my?
Also for us.
What? Okay. I don't know how to. Okay, I'm sorry for that. Let's see how could. Maybe I should make disappear this bar. Let me differently you. Could put this. No, it's not here. This is a matter. It's not related to this.
Professor.
See, any.
Try and stay in the presentation and press the button F11.
Okay. Let's see. Actually, it went without doing anything. Okay, now it's complete. It's okay. That's good. So you should see now the entire slide.
Right.
Okay, thank you. So let's see what are the differences instead for an integral balance for a batch process. Of course, also in this case is a very simple example. So let's consider a tank that is charged with 100 kilogram per hour of water. Calculate how much water is charged after 3 hours. Okay. Now, in principle, this is we can apply the general balance equation, but we have to consider only some of the terms that are appearing in the general balance equation. Because in this case, if you look at the picture, we do not have any output stream. We don't have generation. We don't have consumption. So we have only that input is equal to accumulation. So, of course, we could write this in terms of differential mass balance as m dot in is equal to m dot acc, staying for accumulation. But of course, we can also pass to an integral mass balance, because if you want to estimate what is the mass accumulated, it is sufficient to calculate the integral between time t1 and time tf of m dot accumulation in the t And this is equal, of course, to the integral between T1 and Tf of m dot in over the T. Okay. Now, of course, this is the general equation to calculate the accumulated mass. And of course, we have the integral because in principle, m dot in could vary over the time. And so with the integral, we would take into account this possible variation. In this particular example, we are considering that instead the mass flow rate of the input stream is constant. And so, of course, we can easily put this quantity out of the integral. And so we have m dot in multiplied by Tf minus T0. Okay, actually it should be T1 or we put all T0 and Tf, maybe it's better because T0 we think of initial time. Let's make it consistent. Okay. Okay, and so in the end we have the simple conclusion that is okay. It's 100 by 3, so it's 300 kilogram. Okay, so this is just to give an example of integral balance on a batch process that is of course related to a differential mass balance, but by integration we obtain in the end the balance quantity that is mass. While in the case of differential mass balance, the balanced quantity is mass per time unit. So this is the main difference if we compare the two examples. Okay. Now, if we want to generalize the procedure, what to do in the case for material balance calculation, we have actually followed the procedure intuitively in the simple example I've shown before, but for the general case we can identify a general procedure what we could be useful to do. So as we've seen, the solution is just a matter of simple algebra. So we have algebraic equation for this case, for the differential balance. So we don't have any differential equation in the end. So the effort is to derive the equation from a process description and to highlight what are the known process data and the process variables that are unknowns. Of course, at the beginning, it could not be so easy to imagine what is the process structure starting from a process description, but we will become familiar with that. So for this reason, I mean, following a procedure could be useful because will help us in doing a step-by-step procedure. So for this reason, it is useful to draw the flowchart of the process starting from the procedure, in which, of course, we can either represent the process units as boxes, so generic boxes, just with a name inside if you want to differ, or a number, a symbol to distinguish the different units. Or we will see that there is also, a graphical nomenclature that will allow us to represent the different type of process units, like reactors, mixers, separation unit, with different graphical symbols. But whatever is the case, boxes or specific symbol, we will have a sequence of process unit and lines with arrows to represent input and output material streams. So, for example, here we have 2 units. We have a process description example. We have a gas containing nitrogen and oxygen combined with propane in a batch combustion chamber, in which some, but not all, of the oxygen and propane react to form carbon dioxide and water. Then the product is cooled down, condensing the water. Okay, so this is the description. Just sentences describing the process. The flowchart is the graphical representation of this process made of 2 units. So we have a first step, that is the combustion chamber. The second step, that is the condenser. Now, in this particular case, we are considering the process as a batch. So this means that the balance quantity here are directly mass or mole, actually mole here. But so there is no reference to unit of time. But of course, we could do similar things also for a continuous process in which we have streams flowing per time unit. Okay, so we have on the left this combustion chamber in which we have propane. Okay, here is a quantity that is 100 mole of propane. Then we have the other state that is oxygen plus nitrogen, and we have the quantity in terms of mole. Then the stream leaving the combustion chamber is a mixture of 5 components. So we still have propane, because propane eventually is not completely converted by combustion. We have 50 mole out of 100. We have oxygen that is less than the quantity entering, because the oxygen is consumed by oxidation reaction of propane. Nitrogen instead is the same quantity entering. We will find it again in the stream leaving, because nitrogen is it's an inert compound. It's not taking part of in the chemical reaction. And then we have the products. The products are carbon dioxide and water from the oxidation of propane. Okay. Then we have a second unit in which there is a cooling of this stream. We are not referring here. There is no clear indication on temperature, but we can understand the physics behind. Okay, we are just considering material balance for the time being, the moment. And so in this condenser, we have 2 different output streams. One is given by a mixture of gases, propane, oxygen, nitrogen, and carbon dioxide, while the water is leaving the condenser as a liquid stream. In fact, it is a condenser, okay? And so here we have the quantity, so of course. Now we can see that in this flowchart, we have moles, okay? And so we can see that in some cases, the mole for each species, for some species, we have that the mole entering are equal to the mole leaving. In some other cases, there is a reduction or an increase of the mole relevant to that particular chemical species. Of course, this is related to consumption and generation term. But what is important to remember here, that we have dealt till now with mass, while here we have mole, is that mass conservation applies, but mole conservation does not if reaction takes place. Okay, so this is an important message to remember, and actually we will go back to this when we will consider material balance involving chemical reaction. In the first part, we will consider only physical transformation without the chemical reaction. But this is the first take-home message, that mass conservation applies always, mole conservation does not always. Okay, depends. If we have reaction taking place, we cannot, if we sum all the moles that are entering in the first combustion chamber, this is not equal to the sum of the mole that is leaving in the output stream, because there is no conservation law for the mole of chemical components. Actually, we will I don't say learn, but because probably you know already, but that there is a conservation on the atoms of elements present in the stream, in case in which we are considering reaction. Okay, but this is not actually the main focus of this slide at this point of the story. The focus was just to say that from a description we can draw a flowchart, and okay, we keep in mind that mass conservation applies. With mole, it's another issue. We have to see something more. Okay, so what is a possible procedure? Once we have drawn the flowchart as a sequence of process units, we could report all the values of the known process variables. So all the known input data could be written clearly, directly on the flowchart. And instead we could report symbols for unknown variables, exactly as we did before with this example here. Here we followed intuitively the same procedure. We wrote all the numbers of known process variables, and we use symbol for unknown variables. Okay. So after doing this, we can use the chart as a scoreboard for the problem solution. So this means that we could eventually fill the information on the chart, making some calculation, very easy algebraic calculation separately. So in this way, the chart is the sheet where we can directly report the solution of the material balance problem. And so it's a clear visualization of what we know and what we have to calculate directly. Now, if we want to write the value, so that is the first step of this advice procedure, so write the values of the known variables, we have also to report the units, of course. And of course, we do this at the location of the stream on the chart. So for example, if we have a stream that contains 21% mole in mole of oxygen and 79% of nitrogen at 320 degrees Celsius and 1.4 atmosphere, flowing at a rate of 400 mole per hour, we can label the stream in this way. So we report the total flow rate, here is in mole, then two pieces of information about the composition. These are mole fraction, okay, because are mole of oxygen divided total mole, mole of nitrogen divided total mole, and then we report also the temperature and the pressure. For all these figures, of course, we need to report the units. Then, as a second, okay, the other thing is that, of course, sorry. The other thing is that we can report the flow rate of each component in case of a continuous process in different way. So, for example, we can report the total amount or flow rate of the stream and the fraction of the components, or we can report directly the amount of the flow rate of each component. I mean, it is the same. So in the first case, we have here 60 kilomole of nitrogen per minute, or and 40 kilomole of oxygen per minute. And this is a complete way to specify the feature of this material stream. But this is equivalent, of course, to report 100 kilomole per minute as a total molar flow rate, and then we report two pieces of information relevant to the composition in terms of molar fraction, that are Y of nitrogen and Y of oxygen, 0.6 and 0.4. Actually, you could say that here we have just two pieces of information. Here we are reporting three. So it seems that here there is one piece of information more than the minimum set. And in fact, this is the case, because if we know that the mixture is formed by two components, it is sufficient to report only one piece of information about the composition, because the other one is just a complementary piece of information. Because basically we know that the sum of the molar fraction has to be equal to 1. So if we know the total molar flow rate and one number related to the molar fraction of nitrogen, the set of information is complete, because 1 minus 0.6 equal to 0.4 will be the molar fraction of oxygen. Okay? So we can find the data relevant to process stream in different way. So molar flow rate or mass flow rate of each species, or information about the total molar flow rate or total mass flow rate, and a number of information related to the composition, that actually in the number is equal to the number of components minus 1. So this is the minimum set of information. So on the whole, if we then add also the temperature and the pressure, we have that the minimum set of information that we need to specify a material stream is C plus 2, as I said before, as I said yesterday, where C is the number of components. Okay, here we don't have pressure and temperature, but we have only the information relevant to components that are C equal to in this particular case. Okay, then the second step is to assign an algebraic symbol to unknown stream variables and write these variable names and their associated units on the chart. Now, in doing this, we can follow some tips, some, let's say, good practices. Of course, it's not mandatory to do this, but it could be useful. For example, what are these possible tips? The first one is, if the flow rate were known and the mole fraction were not, the stream might be labeled. Okay, so this means that it could be useful to report the mole fraction if they are not clearly known. The second, we may ultimately have to derive and solve an equation for each unknown that appear on the chart. Of course, it could be an advantage to keep the number of labeled and unknown to a minimum. So this means to avoid to have redundant variables in the case in which the possible additional variable could be expressed as a function of an already reported variable. So this means that if we know, for example, that a mass flow rate of stream 1 is half of that of stream 2, instead of reporting on the chart m.1 and m.2, if appearing as two unknown variables, since we have the flow ratio between the two, we could report this in terms of a single unknown, that is, for example, m dot. So m dot for the stream number 1 and 2 m dot for the stream number 2. Also, the other tip is related to the composition. Following what we were saying before. So if we are labeling the mass or the mole fraction, it's not necessary to label all the mass fraction or the mole fraction of all the components, but it is sufficient to do it for all but one fraction, considering that the sum of all the mole fraction is equal to 1. And so the last mole fraction that we would like to report, it could be expressed as 1 minus the sum of the others. So this is these are tips that are useful to highlight quite immediately on the chart what is the number of effective unknowns to calculate from material balance calculation. Now, let's also consider a bit, let's make a short recap on notation, because notation, of course, is important. Till now, for the variety of example, but it's important to set the notation consistently, considering that, of course, if you look at different books, different scientific papers and so on, you will also some variation with respect to this, so it's not universal, but we can agree internally on this notation in order to have a common way, a common set of symbols. Okay, so for mass, for moles, and for volume, and also for the mass flow rate, molar flow rate, and volumetric flow rate, we can use this symbol. Then, for example, for mole fraction, we can use, till now we have used only Y, but it's a common notation in process engineering to use X for the mole fraction in liquid stream and Y for mole fraction in vapor or gas streams. Eventually, if you are dealing with instead with mass fraction, we also introduced this, we could use, for example, W in small letters. Okay, so let's see what we can do now is to make an exercise together, starting from a description. So we have a process unit description, and from this we want to draw and label a flowchart of the process, and then calculate all the unknown stream variables. Okay, so what is the description? We have a process unit which requires an environment of humid air enriched in oxygen. We have 3 input streams that are fed into an evaporation chamber to produce an output stream with the desired composition. So stream A is liquid water fed at a rate of 6 centimeters per minute. Stream B is made of air, and as you know, is the composition of air is 21% in mole or in volume of oxygen. The balance is given by nitrogen, so we neglect minor components like argon and other stuff. Then there is stream C, that is pure oxygen with a molar flow rate 1/5 of the molar flow rate of stream B. So here we have an information that is not explicit, but is given in terms of a sort of flow ratio. So is the ratio between this stream and the stream B in terms of mole. Okay. Then we have also a piece of information regarding the output. And so the output gas is analyzed and is found to contain 1.5 mole% of water. So this is actually one way to express the humidity of the air leaving this evaporation unit. Okay, so we have information about input as some information about output, but how we will see, these information are not complete, but should be sufficient to set the material balance problem and to calculate the process variable that are unknown. Okay, so let's try to do this first exercise together. So for this, I will use a board. It's already here. So I'm using OneNote. Okay, so let's try drawing. So we have, first of all, we have a process unit. Okay, so let's draw a box in a very simple way. And then we have 3 streams entering, what is called A, B, and C in the, let's do it in a different way. Sorry, pardon, because different A, we don't have enough space to write. Okay. And I put third input here. And then we have 1 output. Okay. So let's maybe we need to go back to this, okay, to see the data. So we have A, that is liquid water, okay, fed at a rate of 20 cubic centimeter per minute. Okay, then we have air, then we have oxygen. Okay, let's put it in a different order, but just of course it's not important. So let's put first the air, for example, for which we know we have information. Okay, we have liquid water. Let's start with liquid water. It's okay. So let's report first what we know. Sorry. So for water, let's assume that this is. So I change the somehow the A. This is A, just for remembering. So we have water entering here. Okay, this is 20 cubic centimeter per minute of water. Okay. Then other information we have on the other two, we have one way to write this. Okay, we have a B air. We just know the composition. So this is the stream B. Okay, for this we have information composition, 0.21 mole oxygen divided by mole. Okay, and then we have the balance given by nitrogen. So the balance means the reminder. Okay. Then we have C, that is the third, for which we just know that is oxygen. Okay. And we know that is with a molar flow rate that is 1/5 of the molar flow rate of stream B. Okay, so this means that we need to introduce some variables that are unknown. That are basically we need to write with simple unknown variables. For example, for B, we do not know the total molar flow rate. We only know the composition. And so we could write N1 dot that are as unit mole of air per minute. And the other information is that the total molar flow rate of oxygen in C is 1/5 of the total molar flow rate of air. Okay, so if we want to express this as a function of the flow rate of the stream B, what could we write directly?
N1 divided 5.
Okay, that is of course the same of 0.2 N1 dot. And this in terms of unit is mole of oxygen per minute. Okay. Then what else do we know? We know something about the output stream. We know that the output gas contains 1.5 mole% of water. Okay. So in terms of mole fraction, what does it mean? 1.5% in mole fraction is equal to? Come on. 1.5% in mole fraction correspond to?
0.015.
Perfect. Okay, so we can write here 0.015 mole of water divided by mole. Okay. Now let's move a bit because this is maybe too close for me. Yeah. I can make this trick. Okay. Now we need to complete the chart with the other unknowns, unknown process variables. So first of all, let's okay. What are the, because till now unknown process variable we wrote is n.1. Okay, that was clearly referred to into the process description in order to assign the molar flow rate of stream C. But what are the other process variables that we need? We say that for each stream we need to have C plus 2 pieces of information, considering that here we have different number of components. So we are mixing basically water with oxygen and nitrogen. So we need to find these three components in the output stream leaving the unit. Okay. So how many other information could we write here? Also in terms of unknown, of course. What is missing in the output stream? We only have the nitrogen. Okay. What else?
Professor, what I did to solving it was found the total amount of moles of water. We have 20 centimeters cubics. We can transform that to moles.
Yeah, this is good, okay, but I'm not looking for the solution right now. I just want to complete the flowchart, then we will go to the solution.
Okay,
it's okay. I'm just saying that the flowchart is not complete. If we want to follow the procedure for which we report first all the known input data that could be referred to input stream or to output stream, as we see, but there are additional process variables that are necessary to close to have all the information about the streams. And so we would like to report these as symbols. Okay, so Verdiana say correctly for example, an information regarding the composition of nitrogen in the output stream is okay. But what else? What do we need also?
Oxygen.
The oxygen, so another information about the composition of oxygen. And then, so if I have only, so for example, we could do, of course, it's my choice which variable I want to use. For example, I could set Y, because this is a gas, Y as the mole of oxygen divided mole. So it's a molar fraction of oxygen. If I want to indicate the molar fraction of nitrogen, I could add another variable. Okay, so this means that this Y could be Y oxygen and Y nitrogen could be another variable. Or following the tips of keeping the number of unknown variables as low as possible, how could I express the molar fraction of nitrogen, considering what we have said before? No clue? No idea, please? Perfect, exactly, this is the way. So this we are considering basically that Y of water plus Y of oxygen plus Y of nitrogen is equal to 1. Now, if we call this Y, this is a known number, we can express, and we call this epsilon 92 equal to 1. From this, we have that epsilon nitrogen is 1 minus 0.015 minus Y. Correct. Okay. And so if we do this, we can report directly here as 0.0 no, sorry, 0.985 minus epsilon minus Y actually, and these are mole of nitrogen divided mole. I could have used colors in order to make distinction between the streams. Actually, I could do this. Maybe I will change it later if I can. Okay, and so these are 3 information actually regarding the composition, but do we need anything else on this stream? No idea. I have all information about the composition. Exactly, the total molar flow rate. that I could report as n dot. I will report as number 3 just because I want to introduce a number 2 for the stream A. Okay, so this is in terms of mole divided minute. Okay, and in fact I could report here n2, sorry, and it's a subscript. N2 dot here as a mole is a total flow rate, but since here actually the this stream is a pure stream of water, it's mole of water per minute. Okay, so basically in this way we have completed the flow chart. Maybe colors would be much better to highlight differences. Yeah, I could rewrite this after. I will do it later, and for next time. So what is the subsequent step now? So we have written, we have drawn the flow chart. We have reported all the input data as numbers, and we have reported as symbols all the process variables that are unknown. So basically, we have as unknown of this problem only n.1, n.2 somehow, even if is easy to derive, n.3 and y. So we have only these for unknown. Okay, actually the unknown n.2 can be determined easily. It's not necessary to consider the material balance equation, because actually we have an information about the flow rate of water in stream A, but is in terms of volumetric flow rate. But eventually we can convert this to a molar flow rate, considering that we know its chemical nature is done only of water. And so this could be the first step to do, maybe the final for today's lecture. That is n.2. From this we want to derive this from the molar flow rate. So this information is what I would call in the nomenclature that I put before. Actually, it should be yes, like this. It is 20 cubic centimeter per minute. Now, if I want to convert this, how could I do? So now, Sebastian, maybe it's your contribution now is
Yes.
is welcome.
We just need to multiply by the density of the water and then divide by the molecular weight of the molecule.
Perfect. That's it. So this means that we enter with this, we multiply by the density of water, and we divide by the molecular weight of water. Okay, so we have to be careful with the units. Actually, in general, I prefer to use international system unit, because in this way all the units are consistent. But for this time, we keep this unit, but we have to be careful. So 20 is okay. It's and let's report also the unit corresponding here: cubic centimeter divided by minute. Then density the density could be convenient to have in gram per cubic centimeter. So we would like to have gram cubic centimeter, and this is for water is 1. And then molecular weight should be in gram per mole. Okay. So considering that this is the denominator, we have mole, gram, and this is okay. Molecular weight of water is easy because oxygen. Okay, you need to maybe look at the element table, but oxygen weight
16.
Wonderful. And hydrogen weighs 1. Okay, so the molecular weight is 18. Okay, and so with this we obtain 1.11, and the resulting units are mole per minute. That is exactly what we need. Okay, so this is just a conversion, it's not material balance. Then the following step will be to apply material balances on different species, either or on the total mass, total moles actually here in this case, to solve and find the process variables that are unknowns. And of course we will continue this next time. If you like, you can do it here on your own, and we will check this on next lecture on Thursday. It's easy, and on the basis of what you have learned till now, you should be able to do this. Okay. Any question?
Not for now.
Okay. So for this, thank you very much for your attention, and I will see you again on Thursday morning.
Thank you.
Okay, thank you, Professor.
Bye-bye.